EV can be flawless on the road, but one bad charge and the whole car goes dark. Today we pull back the plastic flap and look inside the charging port, that tiny innocent opening that connects your car to power. It's not just a hole with a plug, it's tangled little ecosystem of relays, contactors, communication chips, and power electronics that all have to behave perfectly for every charge. If one piece fails, what seems like a simple repair can quickly become an expensive, month-long nightmare. I'll walk you through exactly what's at risk, which parts are most fragile, how an overvoltage or a bad connector can start a domino effect, and why this matters to everyone who owns or plans to buy an EV. Hello everyone, I'm Shayan, an engineer specialized in electric vehicle development. Think of the charging port as a mini power plant interface stuck on the side of your car. When you plug in, a handshake happens. The charger and the car communicate, negotiate voltage and current. And then the physical power path closes and energy flows. That handshake is controlled by small chips and control lines. The power path is handled by relays and contactors. And the energy itself is routed through rectifiers, MOSFETs, and sometimes a bulky onboard charger. Every one of these parts is a potential failure point. Let's break down the charging ports ecosystem in plain terms. First, there are communication modules, the tiny brains that tell the charger how much current the car can take. If these microcontrollers get fried by a surge or a short, the charger may send the wrong voltage or fail to stop when required. Next, the contactors and relays are physically gatekeepers. They open and close heavy current paths. They wear out from cycling, they can weld shut under high current, and they can attract corrosion in salty climates. Then the power electronics. Rectifiers change AC to DC, MOSFETs act like the fast electronic switches controlling power flow, and the onboard charger orchestrates the conversion and safety checks. If a MOSFET fails short, suddenly components downstream see voltage and currents they were never designed to handle. Now picture a typical failure scenario. A driver plugs into a public charger that has a loose pin. The contact isn't clean, so the connection arcing generates heat and a small spike. That spike hits a communication chip, which misreads the voltage and tells the charger to push more current than the port's relays were prepared for. One relay welds closed, a MOSFET overheats and goes short. The onboard charger trips, and tiny ceramic capacitors vent. What started as a loose pin turns into a chain of damaged components that now require deep diagnostics and board-level replacement. That's the cascade effects in action. Which parts are most likely to fail from overvoltage or poor connection? Rectifiers are sensitive because they see raw AC and must turn it into smooth DC. A sudden spike can punch through their junction. MOSFETs are vulnerable because they tasked with fast switching under heavy current. They don't like voltage spikes and can short. The onboard charger, which is essentially a collection of power electronics and control circuits, often takes the biggest hit because it sits right in the middle, exposed to both the incoming power and the battery. The contactors and relays may survive electrically but suffer mechanical damage that leads to future failures. Even parts you'd never think about, tiny TVs, diodes, isolation resistors, communication transceivers, can be the first to die and then they cause the cascading faults. A real-world anecdote that engineers swap in meetings is worth repeating. A fleet operator reported a sudden wave of expensive OBC failures tied to one model of public charger. The root cause? A manufacturing defect at the charger's connector caused intermittent arcs. The arcs generated high-frequency noises and transient overvoltages. Those transients jumped in the isolation barrier inside the OBC, damaged components on the low voltage side, and forced full OBC replacement. The cost to the fleet owner wasn't just the parts, it's the downtime, tow fees, lost service hours, and warranty headaches. That's the domino effect measured in cash and headaches. Here's the big challenge. Charging ports are small, exposed, and used by millions of different chargers and cords. They must handle physical abuse, weather, and a wide range of electrical environments, all while keeping the battery and the user safe. The vulnerability is amplified by three realities. First, the charging ecosystem is fragmented. Many charger makers, many standards, lots of older, poorly maintained hardware in the field. Second, EVs are getting more power. Megawatt class charging is on the roadmap. And higher power means smaller window for error. Third, consumers expect plug and play simplicity. So hidden complexity becomes a surprise when something goes off. Another problem is diagnostics. When a fault happens, it's rarely obvious which component failed. Did the relay weld? Did a MOSFET short? Did a transient kill a control chip? Modern EVs have better telemetry, but many failures still require opening the pack or dismantling the OBC for trace level diagnostics. That takes time and expertise most repair shops don't have. The result? Cars sit in shops waiting for specialized technicians and rare replacement boards. So, how do engineers and manufacturers fight this? There are several layers of defense, and the best designs use them all together. First, robust hardware design. Use components rated for surges higher than typical grid events, and add isolation barriers and use protection networks. Gas discharge tubes, TVS diodes, and high energy surge suppressors to clamp spikes before they reach sensitive chips. Design contactors with redundancy. Use contact materials that resist welding and specify sealed connectors that minimize arcing risk. Mechanical designs also matter. Galving, contact geometry, redundant pins, and spring-loaded connections can reduce the chance of intermittent contact. Second, better communication and smart negotiation. If the charger and vehicle exchange richer data about connector state, temperature, and contact resistance, the system can back off current more gracefully. The instant a problem starts. Imagine a charger that senses a slight contact resistance increase and reduces current for 1 second. An arc is prevented, nobody notices, and the charge completes normally. Some smart softwares reduce the stress on hardware. Third, pre-charge and soft start logic. Many EVs use pre-charge circuits that slowly ramps voltage across the input capacitors to avoid inrush currents that can harm rectifiers and MOSFETs. These circuits include current-limiting resistors and controlled switching sequences that prevent sudden voltage across sensitive components. Improving pre-charge algorithms and adding redundancy here reduces the chance of initial component stress. Fourth, modular, repairable designs. Instead of embedding the entire power stage in one sealed unit that must be replaced, design the onboard charger and input stages as modular boards that can be swapped quickly. That helps fleets operators and repair shops get cars back on the road faster and reduces cost. Fifth, better standards and field maintenance. The industry needs tighter compliance checks for public chargers and better inspection regimes. Connectors and cables wear out. A worn pin is a real hazard. Regular field testing, certification renewals, and clear quality thresholds would reduce the number of marginal connectors causing problems. Sixth, telemetry and predictive maintenance. Cars can log micro events. Tiny voltage spikes, slight increases in contact resistance, flickers in CAN messages. Upload those logs to the cloud, analyze fleets for patterns, and call a preventive recall or service before a catastrophic failure. This moves the battle upstream. Seventh, training for the first responders and mechanics. When a charging port related failure happens, the right diagnostics and repair path can save time. Training simplifies triage. Is it an OBC failure, a simple relay, a connector arc? Clear guides and diagnostic trees can cut repair times dramatically. Here's the moment that matters. One failed part can go from small to systematic in seconds. A fried MOSFET might look like an electronic casualty, but because it's not power path, it can let current flow into places that never expected it, frying the rectifier, blowing charge capacitors, and sending high voltage spikes across the control network. This is the domino effect, not theory, but field-proven reality. That's why the most resilient EVs are the ones that assume failure will happen and design for graceful degradation. Isolate the failure, switch to safe mode, notify the driver clearly, and prevent further damage while keeping diagnostics information intact. A powerful example. A manufacturer designed the charging port and OBC so that if a pre-charge failed, the system physically isolates the input from sensitive control electronics and reroutes telemetry through a separate, hardened path. When one fleet encountered a batch of faulty public chargers that produced micro arcs, those vehicles locked the event, throttled charging to a safe level, and completed charging at reduced speed without losing major components. The fleet incurred small, slow chargers instead of massive rebuilds. That design choice, planning for failures, is the difference between a small inconvenience and catastrophic repair bill. In short, the charging port is not a simple plug. It's the junction of high power and delicate electronics, a place where software, hardware, and human behavior meet. Overvoltage, loose connectors, or single failed MOSFET can trigger a chain reaction that damages rectifiers, melts contactors, and kills onboard chargers. The fix is layered. Better hardware, smart negotiation, robust pre-charge logic, modular repairability, improved standard for field equipments, predictive telemetry, and training for repair crews. Think about charging port as a system, not just a hole on the side of the car. We get safer, more reliable EVs, and far fewer surprise bills. You can learn more about the charge port related failures in the free PDF that I prepared for you. You can click on the link in the description. Thank you.